So my name is Jerry Frankel, and it's really my great pleasure to have the opportunity to introduce Philippe Marcus as this year's Olin Palladium Award winner, to give his address. So Philippe is a professor at the École Nationale Supérieure de Chimie de Paris, which is known as Chimie ParisTech in Paris. He's also the director of, and I think I'll stick to English here, the Director of Research at the National Center for Scientific Research, as we know it as CNRS, and he's the head of the research group of physical chemistry and surfaces. So Philippe got his PhD in 1979, and he did his work at CNRS, and his whole career has been there. That doesn't sound very adventurous, but I have to admit that if I spoke French, I'd live in Paris too, so I don't blame him. So I've known Philippe a long time. I think we've agreed that we met in 1983 when he visited Boston. I was a graduate student at MIT. And since then, we've had the opportunity to meet regularly at beautiful places around the world, as we can only do through this scientific career that we have. Oftentimes at ECS meetings, and also including a couple of summers where I had extended stays at his lab in Paris. So we share a passion for corrosion, and I think that passion, it was even an exhibit last night when we had let's say, animated discussion. It's always a pleasure to talk with Philippe, because I believe that he's really the world-leading corrosion scientist at this time, and that's why he's appropriate for the Olin Palladium Award. So Philippe has been active in a broad range of topics in corrosion, including fundamental studies, experimental studies, and theoretical studies related to corrosion mechanisms, and we'll hear about those in a few minutes. But he's also has covered the spectrum of corrosion to very practical aspects of corrosion protection. I think that Philippe it's agreed upon that he's a leading proponent of taking surface analytical techniques to use for studying corrosion problems. So he's used XPS and Auger and time-of-flight SIMS and scanning probe microscopies. And of course, there are many of us who use these techniques, but Philippe was either among the first to do so or basically set the standard for showing us how to do it the right way. Of particular note would be his work in scanning tunneling microscopy. So it's really hard to get atomic resolution with STM in situ, but Philippe's group has mastered that, and it's led to discoveries that's really placed him as the world leader in corrosion at the nanoscale. So he's also led the way in atomistic and molecular modeling for corrosion science. So for instance, he's studied the adsorption of chloride at defects in surfaces. Using ab initio density functional theory and kinetic Monte Carlo types of modeling. So he's studied the adsorption of oxygen and the effect of oxide thickness on oxygen reduction kinetics. So I think this work has been pioneering and foundational in this field that is now really taking off. Of course, as I said, he's been active in more practical and applied areas of corrosion, including biocorrosion, surface pretreatments and conversion coatings, atomic layer deposition of protective coatings, and also aspects in batteries. He's published about 300 papers in peer-reviewed journals and 32 papers in ECS journals. Philippe has also I think, been a leader in the field in that he's published a number of important books and organized many conferences. So, as it turns out, he's very skillful at organizing conferences. If you've been to any of those that he's organized, you know that. And I've come to realize that probably his most refined skill is actually sort of standing up like this and ad-libbing in front of people. So if he were giving this introduction, I'm sure it would be much better than what I'm doing right now. It's impressive, I always find, when someone has a really good sense of humor in a second language, which he is able to pull off. Well, as a result of all of his technical accomplishments, Philippe has received a number of awards. He's the Fellow of the Electrochemical Society and also ISE. He's won the big 3 awards in corrosion, including the ECS Uhlig Award and the Whitney Award from NACE and the U.R. Evans Award from the British Institute of Corrosion, that's what it is, and several awards from the European Federation of Corrosion. But this one, I think, will be his most prestigious award. It is the top technical award given by the Electrochemical Society, and I think only appropriate that it goes to Philippe. So please join me in welcoming him for his talk on corrosion mechanisms at the atomic or nanometric scale.
Well, thank you very much, Jerry, for this very kind introduction. I can see around here many known faces, colleagues and friends, and of course, Jerry counts as, of course, a colleague and a very good friend. Of course, it's an honor to receive this Olin Palladium award. As Jerry indicated, it's considered as the most prestigious award of ECS. So of course I would like to start by expressing my sincere thanks to the Electrochemical Society and to all those who have been involved in the nominating and selection process. I was told that it's a difficult, very selective process, and of course you need to have some supports on your scientific activity to do that. I came, as Jerry said, I came for the first time, I think, to give a talk. I had been to the US before because I worked for a while at Kodak Research Labs in Rochester, but my first talk that I gave in this country was in 1983, and as Jerry said, that's when I met him, because after I went to an Electrochemical Society meeting, and after that I had an invitation from Ron Tennyson to give a talk at MIT, and that's when I met Jerry. At this first meeting of the Electrochemical Society, I met 3 big names at that time, who were Jerry Kruger, Bob Frankenthal, and Hugh Isaacs. And today we are also we are having this symposium also as a memorial to Hugh Isaacs. And this is very important for me because, okay, I'm not going to talk about other important persons that I've met in my career, including, of course, in France. But as I'm in the US, I would like to emphasize that this was very important because in the US you can meet big names, and they will talk to you very easily, and they also will support you and encourage you, and it's not always like that, at least at that time in Europe. It was much easier in this country. And also I met these 3 persons, and that was very important because, you know, Jerry Kruger, for those of you who have known him, and there are quite a few in this room, if I can judge from the average age of these participants, he was looking, Jerry Kruger was looking at things from, say, material science, a material characterization perspective. And Bob Frankenthal was looking at things essentially from a surface analytical point of view, you know, using, at that time he was developing the use of Auger spectroscopy. And Hugh Isaacs was looking at things from an essentially electrochemical perspective. And my experience in France was to have supervisors like Jacques Bénard, Jacques Houdard, who were looking at things from a metallurgical point of view for the first one and from a surface science point of view for the second one. And I think corrosion is just about trying to bring all these backgrounds together and then look at phenomenon. Another thing is that Jerry Kruger said one day that doing research is like traveling in the same landscape but with different eyes. And actually this was a citation from a French writer, from Marcel Proust. And that's what he said. And it was true, but I had some difficulties to find in which book he had said that. And I think it's very true that we are looking at things that people have already been looking at, but with different eyes because we have different techniques. And because we have different techniques, we have also new ideas. Okay, so now back to the Olin Palladium Award. And because it's late and I'm sure you are also looking forward to some entertainment after my lecture, I should try to also entertain you a little bit. And that's why I showed you the medal that I received yesterday at the plenary session. So that's the Olin Palladium Award medal. I brought a picture because it's made in palladium, so it's now in the safe of my hotel room. So I thought it would be risky to bring it today. And this shows, for those of you who don't know, this shows the goddess Athena. And I'm going to tell you in a few words the relation between Athena and palladium. But before that, I want to tell you that Athena, which is a Greek name for the goddess of wisdom and war, the Latin name is Minerva. And she was born from the head of Zeus. You may know that. But perhaps you don't know why. And the reason is that this time of the day, I think we can talk about that, is that Zeus laid with Metis, a goddess. And he was afraid that she would become pregnant and have a son or a daughter that would be better than him and would take his place. So he swallowed her. But she was already pregnant, so Zeus gave birth to Athena, and she came out of his head just like that, with, grown up and with the armor. And the shield is actually the seal of the Electrochemical Society. Now, interestingly enough, on this medal, there are also the elements. And when you do corrosion, of course, it's very important because this is the water. So there could be aqueous corrosion. This is the air, atmospheric corrosion. This is fire, so high temperature oxidation. And this is the earth, so maybe bio corrosion. Now, the relation with palladium is that Athena, when she was playing as a little girl, she was playing with a half-sister, Pallas. And they were playing at fighting, and unfortunately, she killed her sister. Things like that may happen among gods and goddess. And the name of the sister was Pallas. So that's why they then called her Pallas Athena, just in memory of this poor sister that she killed while they were just in the playground. And the palladium comes from the name Palladium, which was a small statue which was supposed to protect the city of Troy. And it was fashionable in the beginning of the 19th century to give a name of a Greek god or goddess to new discoveries. And this was the case for the new metal that was discovered that was named palladium. So this is the story, maybe a long story, to explain the relation between Athena and palladium. And Athena is the goddess of rational thoughts. So for being a French and having been educated from the philosopher of the 18th century, I'm very proud to get a medal that is embodying rational thoughts. Now, some people ask, what matters in your research work? Of course, there is no recipe to get an award like this one, but I thought maybe I should write a few keywords, and I think that, but unfortunately, what I'm going to say now should be directed to PhD students, not to senior researchers, but the PhD students, they have their poster session at the same time, so I'm afraid there are not too many here. So if I meet them later, this is what I would say. I think we need a vision, and of course my vision, as was said by Jerry, is that we have to look at corrosion at the nanoscale, because that's where the initiation of reactions take place. So if we could stop corrosion at this stage, then we could get rid of corrosion. It's always very difficult to stop corrosion when it's in the propagation phase. Anyone doing localized corrosion or stress corrosion cracking would know that. Now you need also to have an approach to which you will stick, and the approach that I have used with my group is to select model systems. Of course, they have to be relevant for what you for the question you want to answer. And then you need appropriate techniques, and including advanced techniques, which we have always tried to use as they developed. And last but not least, you need a good team. And although usually we acknowledge our team at the end of the talk, I think that for an award, it's appropriate to do it at the beginning, because without a good team, I would not be here without a good team. So this is a picture that was taken not so long ago. And actually, I've showed this picture already, and some people say, what I see on this picture is that you are surrounded by nice girls. And I had never realized that. But it's not what I want to show. What I want to show is some people that in a team, the team is important, but some people count more than others. And I would like to say that Vincent Maurice is, I wouldn't be here without him, because he's the one that is co-supervising all the work on scanning tunneling microscopy and scanning tunneling microscopy. And also, Antoine Seyeux is the expert in tough seams, and Sandrine Dana is the expert in XPS, and Dominique Costa is the one doing the DFT calculations and so on. So yeah, of course, these people have been very, very important in the course of my scientific career. Okay, so now corrosion mechanism at the atomic and nanometric scale, because that was the title and still is the title of my lecture. So I'd like to review a few aspects that are related to the role of the surface structure and composition in corrosion processes with emphasis, although as Jerry said, we've been looking into many other problems, but I will emphasize probably passivity and localized corrosion initiation. So we need to understand corrosion mechanism, we need a higher resolution investigations of surface reaction, and the surface science approach that we have been using is, of course, quite appropriate for that. So I'm going to show a few data that are based on the application of advanced in situ and ex situ surface analytical techniques, such as scanning tunneling microscopy, scanning tunneling spectroscopy, XPS, tough seams, which are always combined with electrochemical measurements, either in situ with STM and STM, or ex situ with XPS and tough seams. And probably I won't have any time to show DFT modeling, but the modeling by DFT is a very important complementary aspect of the research we are doing. Well, I think you all know here that when you do STM, you use a tip that you get close to the surface and scan it so that electrons tunnel from the surface to the tip or vice versa. And this technique provides maps of the electronic density of states. And the electronic density of states is localized on atoms. So ultimately, we have a map of the position of atoms. And the beauty with this technique is that you can use it in vacuum. That's what we do for some application. You can use it in a gas, we also do that, and you can use it in liquid because if you insulate most of the tip and just keep the tip of the tip uncovered, then you can simultaneously record the tunneling current between the surface and the tip. And if you have two electrodes, you can record simultaneously the current potential curve. So you can do electrochemistry under controlled potential and current conditions, and at the same time image the surface with atomic resolution. And contrary to other techniques like scanning electron microscopy, what we get is a 3D image of the surface. And we get it in the real space, in contrast with what you would get by doing X-ray diffraction. So using these techniques, we look at a number of problems. And of course, if you are interested in corrosion, you are interested in what happens when you expose a metal to water. So the first question we wanted to answer was what happens if you take a metal surface, expose it to water? Do you get some sort of order at the surface, or do you have a completely disordered layer? When we started this work, most people believed at that time that because it was in water, everything was not well organized, so that is essentially disordered. And we found out that this is not at all the case. We looked at a number of metals, and this is here copper in alkaline solution. And if you scan the potential and look at under potential with respect to the oxidation, that is in the range where you see nearly no current, except if you enlarge, and then you will see only adsorption of, so it's a process where you have adsorption of the OH from the water to the metal surface, and this takes place at under potential with respect to the oxidation of copper. And then if you look at the surface in situ, you find this extremely well organized and ordered surface where you have the copper atoms and the OH from the electrolytes come to this high coordination site, and they formed a very well ordered structure. So the message here is that if you put a metal surface in water, you get an ordered layer of dissociated water molecules that is very much related with the structure. So it's an epitextual relationship between this layer. And actually, this is important to understand passivity because this has exactly the structure of one layer in the oxide that would be formed if you then increase the potential. So it's a precursor to the formation of the oxide. So that the oxide that is forming has the memory of this structure which is formed at potential which is below the formation of the oxide. And we looked at something similar on different metals. So we looked at silver, and again we find this order. This is a more complex structure. This is a very simple structure. This is more complex, but because the unit mesh is large, but this is the same message, is that you form a very well ordered layer. And we did it also on nickel. And nickel is slightly different because from these two we could think that it would be the same on all metals, but it's actually not the case. If you look at nickel, you have a structure which is not as well ordered. You have a local order here, and in other areas it's disordered. And we believe that this is due to the fact that we have only a partial charge transfer between the OH minus and the surface. So there are subtle differences between metals, but in all the cases you get a fairly well ordered structure. And now the other thing, of course, that we've been looking at in many details is the passivity of metals and alloys. So this is just a textbook description of what a passive layer is, but of course the key issue is the stability for the corrosion protection. And actually, beyond this textbook definition of a passive film, there are many questions which are even now not completely answered. And this is some of the questions. What is the oxide structure? What is the surface hydroxylation? What is the interface structure? What is the effect of the potential and time on the structure? What is the nature of the defects? Do we know the growth mechanisms? Do we know enough about ionic transport? If we have an alloy, what is the enrichment of alloying elements and what is the process leading to this enrichment? What are the local electronic properties of such a layer? And of course, what are the initiation sites for localized corrosion? So there are many questions, and we tried over the years to answer these questions. So to do that, of course, you need model systems, but if you have picked up the right model, then when you have the answer to the question, this can be applied to even much more complex systems. So again, because this is an award lecture and not just a regular presentation, I can start by the conclusion, which is very, very nice. You know, usually people would say, well, why did he give the conclusion before the data? But when you give the Palladium Award, you can give the conclusion. I could even show no data and no one would complain. But I'm going to show the data proving what is written here. Passive films are crystalline. There may be exceptions, but they are, most of them, I would say, are crystalline. There is an epithelial growth on metal substrate. So you cannot understand the behavior of the passive layer if you don't know what is the influence, the effect of the surface structure. Usually the passive films will naturally minimize the interface energy, and that means that the way they will grow, the nature is made in such a way that the way they will grow will minimize the interface energy, and it will also minimize the surface energy. And this minimization is done by a tilt in the direction of growth of the oxide with respect to the metal. And that, of course, you can observe only if you control the structure of both the surface and the oxide. And the surface energy is minimized by hydroxylation, and to know that you have to use methods like XPS, for example, that will tell you how much hydroxyls you have on the surface. So we looked at, we did experiments along this line, and we looked also at copper, but now we are no longer talking about the under potential range, but when you go into the formation of the oxide, so this is a cyclic voltammogram for copper. So we looked at the potential over this range of potential, and this is a typical image that we get, and that's the high resolution image. So we have really atomic resolution. This is a non-filtered image, and it's recorded in the aqueous solution. So we know that the film is crystalline, but we have these fairly narrow terraces and steps, and this is the model, and you see the tilt between the planes, the dense planes of Cu2O and the substrates. And we can determine this tilt by looking at the width and height of these steps. And this is just a few degrees, 5 degrees in that case. And this is exactly what you need to optimize the position of atoms at the interface. So again, that's the nature is doing that. We don't have to do it by processing the surface. This is done naturally. So crystallinity and epithelial growth and interface energy minimization is already observed here. And the layer of OH, this is not derived from in-situ STM. This is derived from ex-situ XPS. And there are also other groups who have seen that even before we did for the ex-situ XPS, like Henning-Streblow, for example. So to make a long story a bit shorter, we did that also on nickel, and similarly crystallinity, and you can also see these very clear features that are characteristic of a crystalline material, although the thickness of these layers are of the order of 1 to 2 nanometers according from XPS, or also according to just reduction of the oxide that you can do at the end of the experiment and just measure the charge. So we know the thickness from the electrochemical measurement and from the XPS. Now on nickel, you also have this tilt between the oxide and the metal, and this is producing steps at the surface. So the substrate is there, and that's the model derived from the STM experiment. So you see that even if you have a very smooth nickel surface, it's a 1-1-1, so it's the most compact and smooth at the atomic level. But however, because of what I've said about the interface and surface energy minimization. At the surface of the oxide, you have these terraces and steps, and they are hydroxylated. And so what we did, and I'm not going to show the data, but then, but Jerry mentioned this work, what we did is that we then did some DFT calculations to look at where these chlorides would react. And actually, not surprisingly, what the DFT was showing was that the chloride would replace the OH at the step edges, so that the initiation of the localized corrosion would be the replacement of these hydroxyl groups which are decorating the step edges. And that would be the initial stage of localized corrosion. And similarly with chromium, you get the most stable surface, which is the basal plane of alpha Cr2O3, where you have the highest coordination of atoms. And chromium is a good model for stainless steel. So of course, on the stainless steel, there will be iron in the oxide. But then we did measurements on stainless steel, and this is what we get. So if you do measurements, we looked at both ferritic and austenitic stainless steels, and this is a typical STM image. So you see, again, the maxima in the tunneling current, and this is the model corresponding to this image. And again, this corresponds actually to the basal plane of chromium oxide. Of course, there is iron in it. We know that, and it was known already from XPS data. So there is iron in this lattice, but this is essentially the lattice of chromium oxide, and it's the basal plane because, again, that's the most stable. So the stability of these layers is entirely related not only to the chemical nature, but also to the structure. So for a given oxide, the structure is the determining feature for the stability. Okay, now we looked at the effect of potential and time, and we saw that if you take an alloy, crystallinity is not instantaneous. It takes time for the passive layer to become crystalline, and we could see that by looking at different passivation time. This is completely disordered. You start to see these nano crystals in the passive layer, and then at the end it's very well crystallized, so that crystallinity takes time. And then we looked at the stability. So we produced these passive layers, and after some time introduced chlorides, and it was clear that the more crystallized, the more corrosion resistant was the oxide layer. Of course, at the same time, there is an enrichment of chromium. So it is both the chemical nature, enrichment of chromium in the oxide, and the crystallinity that improve the stability in, say, chloride solution. Okay, now I'd like to show some measurements that we have done on looking at ionic transport. It's another big question. How do these films grow? There are many models around, starting from the time of Carl Wagner, but it is still a big question. There is still a big question mark. How do the film grow? And you know, essentially, you could think about ionic transport by, say, oxygen vacancies or cation vacancies. So how can we find out what are the ions that are transported? And to do that, we have used time-of-flight SIMS, which is essentially a technique where we can analyze with, it's a dual beam technique, so we can analyze with an extreme surface sensitivity. It's much more sensitive than XPS. We can analyze the surface with one beam. Ions are emitted in the time-of-flight spectrometer, so we can analyze the whole periodic table quasi-simultaneously, just looking at the time that ions take to fly in the analyzer. And with another beam, we can, cesium beam, we can make depth profile. So we would record for any species, we could record the intensity as a function of depth so that we could look at this. And of course, we can, and because we analyze the mass, so we can use isotopic markers. This has been done in the past. We were not the first to use isotopes. For example, in the corrosion community, Mike Graham and his group, they used oxygen-18 already a long time ago with static SIMS. But now we have the time-of-flight SIMS, And what we did, which had not been done before, is that we implemented on the tough seams the possibility to do in situ oxidation with either oxygen 16 or oxygen 18. And just as a sort of proof of concept, the first experiment we did in situ was to take a chromium sample, oxidize it in oxygen 16, stopping the oxidation, very quickly changing the oxygen 16 to oxygen 18, and then all that in situ, and then looking at where the oxygen. So this is here a depth, an in-depth profile. This is the signal of oxygen 16 and the signal of oxygen 18 after this two-step experiment. And you see there is absolutely no ambiguity. It's very clear that you find the oxygen 18 in the inner part of the oxide. So this gives a direct evidence that under the conditions of this experiment, the oxide is growing by diffusion of oxygen. And this means that we have oxygen vacancies in this oxide film. So on a pure metal, it's fairly easy with, now with this equipment to look at problems like that. Of course, it's more difficult if you take an alloy, but it's, however, feasible. And we've been looking at the same problem, but looking at a more complex alloy, which is a nickel-based alloy 600, which is very much used in the nuclear industry for making a steam generator. So this work was funded by EDF, which is the French electricity company. And what we were looking at was exactly what I said. How do the layer grow? So how can we do that with isotopes? The way we do it is that, again, we do this two-step experiment. But now we do the first oxidation in water at high temperature. So this is done in an autoclave in this collaboration with EDF. And then we look at the oxide formed by XPS, tough seams, STM, or whatever. But then what we do is that in the tough seams, we can now re-oxidize the oxide using oxygen 18 and look at where the oxide is forming at the beginning. So we did that, and so these are profiles where I'm not going into the details, but from these profiles, you can, this is after the first oxidation in water at high temperature, and these are for short time. So this is a special autoclave that allows us to do short time experiment at in high temperature water. So I'm not going into the details, but from all of these profiles, we can already come out with a model of the film with an outer layer rich in iron and nickel, and an inner layer rich in chromium oxide and the spinel, NiCr2O4. But that's not what I want to show now, but this is already a very important result. And we can also look at the kinetics, because if you look at this signal, this is the signal of ions Ni2-. So this is the substrate. So when we come on this flat part here, it means we have the interface. So we can precisely locate the interface. So if we do that as a function of oxidation time in high temperature water, we have the kinetics of oxidation. We can analyze the oxide by combining XPS and tough seams. Now to look at the ionic transport, in the tough seams, we re-oxidize this with oxygen 18. And then we look at the profiles, and we can see that all the species containing oxygen 18 are found in this part of the layer. So this is a direct evidence that this oxide grows by diffusion of anions, so there are oxygen vacancies. And because this can be shown after a very, very short re-oxidation time of the order of, say, 1 minute, we can reasonably assume that what we are really probing are the defects existing in this oxide when it's in high temperature water. Okay. Now we can look at numbers, so we can look at in details at the oxygen profiles. I'm not going to go into the details, but I would like to draw your attention to the fact that there is a slight complication here. Is that these profiles, this is oxygen 18, and this is oxygen 16, sorry, and this is oxygen 18, and this is for other exposure time. So let's disregard that. But you see that these profiles are not straightforward to interpret. And the reason is that you have not only solid state diffusion of oxygen or oxygen vacancies, but of course you have also isotopic exchange. So there is no technique is perfect like human beings. So we have to now take into account that at the same time we have diffusion and isotopic exchange. So we have to do some mathematics to fit and interpret the data. So on one hand, we have the solid state diffusion. So this is just expressing the Fick law, and I think a good book for that is the mathematics of diffusion from Crank. But then we also need to take into account the isotopic exchange between oxygen 16 and 18. And so we come out with this equation here, which we call the modified Crank model, which is a modified Fick equation, taking into account the isotopic exchange. And then we can fit the Toff-Sims profile. So these are portions of the profiles I've shown before that were renormalized. And then the black dots are the experimental data from the time of flight Sims, and the red curve is the fit using the equation I've shown before. So from that, we can not only find out what is the species that is diffusing in the oxide, but we can calculate the diffusion coefficient. And it's very interesting because not only we need this number to predict the evolution of the oxide in a nuclear power plant, but we need to know whether this number will vary with time or not. So we did measurements like that after different oxidation times in water. And then if we look here, which is for longer exposure time, we find a different value. In the first case, we find a value of the order of 10 to minus 17 centimeters squared per second, but in the other case, we found 10 to minus 19. And we check this data. So what's going on? What's going on is that at the beginning, we start to form chromium oxide. And we know that from both the XPS and the Toff-Sims. But with oxidation time, we then start to transform the chromium oxide into the nickel chromine, the spinel, NiCr2O4. And the diffusion coefficient is not the same. So now we can do this kind of measurements and plot the diffusion coefficient as a function of oxidation time in high temperature water. And we see that we start from this value, which is very close to published values for chromium oxide at this temperature, and then it goes down with oxidation time, and it sort of levels off at a value which corresponds to the diffusion in the spinel. So if you want to model the behavior of such an alloy, you of course have to know this data, because in any model, you will have the diffusion coefficient of the species responsible for the oxidation. Okay, I guess I have soon to conclude. So I'd like just to show now some data. I have shown some data using STM, using Toff-Sims. I'm going to skip the density functional theory calculation. I think DFT is nice in the morning, but you know, when it gets late, it gets a little bit boring. So I will skip the DFT. Don't tell my coworker that I did that and say that. She would be unhappy. But I'd like to show some data on the electronic structure, local electronic structure, because this is directly relevant to localized corrosion initiation. Using the same technique as STM, so we move this tip over the surface. But of course, the nice structure I have shown at the beginning of this talk is the structure that we measure on top of grains, oxide grains on the surface. But of course, we have many, many grains. The grains are not that big. They grow with potential, they grow with time, but they remain fairly small. So we have, of course, grain boundaries between these oxide grains. So we wanted to know whether we have a different electronic structure at the grain boundary. And there is virtually no technique that can answer this question, except if you use the tip of the STM, and then at each position here, you stop the scanning, and then you ramp the potential between the tip and the surface. So now you are no longer doing scanning tunneling microscopy, but you are doing scanning tunneling spectroscopy. So at any point of the surface, we can record the density of electronic states at this point of the surface with a resolution, which is the resolution of the scanning tunneling microscope, which means better than a nanometer. So we can really look at grain boundaries. So we did that, and we did that we started with nickel because we have a lot of control, we have good control of the structure. So this is typically what we get. So we measure so what we get at the end after some mathematical treatment of the data, we get here the density of electronic states as a function of energy. So it's not the electrode potential here, it's the energy. So we have the Fermi level here, and we have here the conduction band starting then and the valence band. So we have a full picture of the electronic structure, and we can distinguish the electronic structure at grains, and this is the average of many measurements on top of grains, and this is the average on many but less measurements, obviously, because there are less grain boundaries than grains on the same surface. And we have these two families of curves, and you see that we can measure the band gap, which is the surface band gap, and that's the one which is important for electron transfers at the solid-liquid interface. It's the surface band gap. So we can measure the surface band gap, and we can also measure the position of the higher level of the valence band. And you can see that there is a shift here. It goes to lower value on grain boundaries, and this is indicative of this downward shift of the valence band edge is indicative of the presence of oxygen vacancies. So that means this proves that we have more oxygen vacancies at the grain boundaries than in the grain. And of course, oxygen vacancies means more reactive, locally more reactive surface towards anions like chlorides. So from that, you could expect that these locations will be preferential sites for pitting. And now, using the STM, we can look at where pits initiate by imaging the surface. And if you do that, this is what you observe. So this is a nano pit. So it's really the initiation stage on a passivated nickel surface. And you can clearly see the grains of the oxide. The substrate is a single crystal. There is no grain boundary in the metal, but you have the grains, you have the 3 grains here. So this is a triple point, and that's where the pit initiates. So it's completely in line with the fact that the local density of states measurements have shown that there are more oxygen vacancies, so that these points are more reactive towards chlorides. And I think that I will stop here. I don't think I need a conclusion. I think if I should make a conclusion, it would be very short. It would be to say that I think that this approach, which is a surface science approach, if you have in mind to understand corrosion at the nanoscale, is, I guess, an approach that was really fairly successful in terms of providing new data for understanding nanoscale corrosion. Thank you very much for your attention.